Hi there, ladies and gentlemen of Chemistry 300 at Downers Grove South High School. This is Mr. Workman. I'm going to make sure that you know how to use graphical analysis to produce a graph that compares milliliters with cubic centimeters, which are two different units we use to measure volume. So the first thing you're going to go ahead and do, of course, is to open up graphical analysis, and if you didn't see that, the icon looks like this. Now on my desktop, of course, I've got more and different icons than you may have, but your graphical analysis icon should look pretty much the same. Now, what we're going to do here, of course, is generate a graph of comparison of data between milliliters and cubic centimeters, and so what I want to do is, of course, make a title that describes what this graph is going to be. And in order to do that, what you can just do is double-click on the graph, and you'll get this graph options window. Another way to find that is to go to the options tab up here and press this selected option, which is graph options. And in the title window, enter your title. And what I just put in there is volume in milliliters versus cm3, which is cubic centimeters. I'm going to click done there, and you'll see that the title populates at the top of the graph. Now what we're going to do is label our axes, our x and our y axes, of course. And in order to do that, there's a couple of ways to do it, but one of the ways you can do it is just to double click at the top of the T table over here. This is the chart where you put in your data. And I'll just go ahead and do that. And if you hover over the x, it even gives you an indication there. It says double click to edit the column. So I'm going to double click there, and you get a column options window, and what you're going to do there is name the column. Well, actually what you're doing here is you're naming the x-axis. And I want volume in cubic centimeters to be the x label on the graph, and I'm going to do a short name, and the short name window is going to be what goes up at the top of the chart here, the top of the column. So I'm going to put volume in cubic centimeters, and then here I'm going to enter the units, which is cm, and then I want a superscript 3, so I'm going to use this drop-down arrow and choose superscript, and then choose the next drop-down menu that comes up, which is 3, and hit done. And what you'll notice is that volume in cubic centimeters, and there's my particular unit, populates there, and then the shortened name populates up here. Now, the numbers you're putting in here are, of course, the numbers that you got from calculating the volume of your objects, whether they were cubes or maybe they were cylinders. And you did that by measuring with a ruler and then doing the calculation. If you measured the side of a cube to be, I don't know, probably 1.2 centimeters or 1.25 centimeters or something like that, you cubed that, of course. You multiplied that number by itself, times itself 3 times. And so the volume of 1 cube, per se, in cubic centimeters should be somewhere around 2.1 cubic centimeters. And what will happen is that once I get a corresponding value over here, the ordered paired data set will populate in the graph. Now, what's going to go on the y-axis, of course, is volume again, but it's going to be volume in milliliters. And I'll make a short name there. And notice I've got the M lowercase and the L capitalized, and I'm just going to put in units again. So my y-axis label populates there, and then the column heading populates here. Now, if you dropped a cube of ever so gently into some water in a graduated cylinder, you would have noticed that the volume in the graduated cylinder went up as the cube descended into the water, and the amount that the volume went up is equivalent to the displacement of that cube. And what that is going to be the volume in milliliters of the cube. And when I put any of these cubes in water, I notice pretty typically that the volume goes up by about 2.1 milliliters, as it happens to be. Now, I had a cylinder that I measured, and then I measured the height of, and I measured the diameter of it, and then I divided the diameter by 2 to get the radius. And then what I did is I input that particular set of numbers into the volume equals pi r squared times height formula for the volume of a cylinder. And for one of the short squat cylinders, I actually measured it and did the calculations. I got 3.4 cubic centimeters. And then when I put that same cylinder into some water, I noticed that the water level raised by about 3.3 milliliters when I did the volume displacement method, or the water displacement method for volume. And notice what I've got here is a data point right here. And if you look at the lower left-hand corner of the graph, so that would be down in this region here, you'll notice that if you leave the cross, your arrow turns into a cross when it's on the graph. The numbers down here indicate the position of the cross. So that data point right there is 2.1, comma 2.1. Now I'm going to move this axis. I'm going to change the scale of this axis by dragging on the axis here and dragging on the axis here so I can more easily find this data point. And I'm going to move my cross to that data point, and then you'll see down here when I have the cross in that position what the data point is. And as you can see, that says 3.399 down there in the lower left-hand corner of the graph and 3.30, and those values, of course, correspond with this ordered pair here. Now, here's another little interesting fact. If I have nothing, its volume is 0 in cubic centimeters, and nothing is also 0 in milliliters. So 0, 0 is a valid data point here for comparing milliliters and cubic centimeters. So I'm just going to throw that in there. Now, I measured another cylinder, and I measured its diameter, I measured its height, and I calculated its volume. And I calculated its volume to be 7.2 cubic centimeters. That cylinder was a little bit taller, but the diameter was the same. And when I dropped it into some water, I noticed, and I dropped it, placed it very carefully into some water in a graduated cylinder, I noticed that the volume level on the graduated cylinder went up by about, I thought, when I looked at it, 7.3 milliliters. Now, that wasn't the total volume, of course, in the graduated cylinder. It was the difference between the initial level and the final level. And so I have another set of corresponding numbers here. And as you can see, my graph kind of has these connected points. This is the first point that I put in. Oh, wait a minute. Is that the first point that I put in? Yeah, it was 2.1, 2.1. The next data point I put in was this one, 3.4 and 3.3. And then the next data point I put in was 0, 0. And then the next data point that I put in was all the way up here at 7.2 and 7.3. And you can see that this red line sort of zigged and zagged back and forth between these data points. And if you don't want that zigzag effect, what you can do is double click on the graph, and then you see where this line is right here and this box is that says connect points. You can deselect that, and then that line, that zigzagging line, goes away. Now what I'm going to do here is see if I can establish a slope for this set of data, and I'm going to do that by choosing the linear fit button. I'm going to click on that, and what happens is when the linear fit operation is used, it gives you this y equals mx plus b, which is the general format for a linear function. The m here is 1.014. The b is, of course, the y-intercept. That's where this line should intercept this y-axis. That's at negative 0.04389, and that's really close to 0. So the y-intercept is really close to 0. And my correlation here is 0.9997, which means that I have a pretty good correlation. If I had a correlation of 1, it's probably as good as I can get. This RMSE value, we're not going to worry about that right now. So what does this really mean? Well, in the notes section here, I can make a little note here. What this really means is that the slope of just about 1 indicates a 1-to-1 ratio or proportion between milliliters and cubic centimeters. So for all intents and purposes, milliliters are equal to cubic centimeters. All right? Again, let's look at this. If my m is essentially 1 and my b is essentially 0, that means my function is y equals 1x plus 0, which is the same thing as y equals x. And since y means milliliters and cubic centimeters is x is cubic centimeters, what that means there essentially, milliliters equals cubic centimeters because of this function, and that function is really defined right here with this information. All right, so what you should know is that I'm not just telling you milliliters is equal to cubic centimeters. This data set and the data set that you all came up with in the lab today and or yesterday is essentially showing you that milliliters is equivalent to cubic centimeters. And that's the essence of science. Scientific information isn't necessarily just something that you know, it's information that has been experienced by someone and reported by someone, and you all experienced this yourself. You, in essence, discovered that milliliters are equal to cubic centimeters. Okay? So that's all for now. Hopefully you understand that milliliters is equal to cubic centimeters and why that's so. And I would pay attention to this information down here, because when you take a little quiz, that's the kind of stuff I'm going to ask you about. Now, of course, for printing options, what I'm going to do is make sure that my print footer is selected and the names of the people working on this graph are there. I actually didn't have a partner here, but if I did have a partner, I would have put that name in. I'm going to click on OK, and then when I go to print, of course, what you're going to do is choose the printer that is appropriate for the room that you're in. Make sure that if you're in room B227 or B225 or one of the other chemistry rooms or other science rooms, make sure that you're selecting a printer that has the room number indicated in the name of that printer. And so when you go to print, you'll click OK, make sure that you're choosing the right printer. And usually the computers that are in those rooms are going to default to the appropriate printer, but it's always a good idea to double check. Okay, ladies and gentlemen, that's it. Hope you learned something.